So we talked about what decision trees are, and we also discussed how decision trees find the features and the values that they are going to use at each node in order to partition the data. So with this information, we are able to explain the decisions that decision trees make at a global level. And this is given by the feature importance that we can derive from the decision trees. So in this video, we're going to address how do we derive feature importance from a decision tree. Let's get started. So here we have a decision tree, and we discussed that at each node, the decision tree will select a feature and a value, and based on whether the observation satisfies this condition, it will take it through the left or the right child, where it will ask subsequent questions. So intuitively, by looking at this diagram, we would think that the feature age is quite important for this decision tree because it was chosen at multiple nodes. And we're probably not going to be wrong. At each node, there will be an increase in the purity of the data, because this is the condition that we're going to use to select the partition. So again, intuitively, features that obtain a greater increase in purity are going to be more important. So without knowing too much about calculations, how often a feature is used in a decision tree to partition the data is an indication of how important that feature is, and how big the increase in the purity after the partition is also an indication of how important that feature is. And one more bit of intuition: when the data is super impure, or basically when we have the entire dataset, getting purer partitions is going to be easier than after diving down the nodes, where at these intermediate nodes we have data that is more homogeneous. So the increase in the purity at top nodes is in general greater than the increase in the purity at later nodes. So again, if a feature is selected at the top nodes of the tree, in general, is also going to be more important than those features that are selected later on in the tree. So with this intuition, when you see a diagram of the decision tree, you are able to tell by eye which features are the most important for this tree in order to make the predictions. But there is also a way to quantify this importance. And quantifying this importance consists in measuring the decrease of the impurity. So if we focus at one particular node, the data here has a certain impurity, which we're going to call node impurity. And as the data is taken through the left and the child node, hopefully in these nodes they will have less impurity, or in other words, more purity. So the importance of the feature is obtained by subtracting the impurity of the left and right node from the impurity of the top node, which is this equation that we have here. Here we have the top node impurity, and we subtract the sum of the left impurity plus the right impurity. And these impurities are going to be weighted by the number of samples at each of these nodes. So this node is going to be 1 because it's the total number of samples, and here it will be the fraction of observations that arrived at this node respect to the parent node, and here we will have the fraction of observations that arrived at this node based on the parent node. And we want to weight the impurities because here we may have a gigantic impurity loss, but if we end up with 3 observations, it's not as representative of the data as a smaller decrease in impurity, but that is true for more observations. So this is the intuition behind this formula. With this formula here, we will calculate the importance of the feature selected at this node, but then the feature might be selected again at a follow-up node, so we need to repeat this procedure and add the importance to the importance that we obtain at this node. So let's illustrate this with an example. Later on in this section, we're going to train a decision tree regression to predict house price, yet again. And then we're going to plot the decision tree that we obtained after training, and we're going to obtain something like this. So this is a decision tree to predict house price. And you can see that scikit-Learn offers a lot of information out of the box. In each one of the nodes, we have first the feature that was used to make the splits, and then the value for that feature that was used to make the split. So here we will have the entire dataset, and if the median income is smaller than 5.029, the data will go to the left child, otherwise it will go to the right child. We also have the sum of the squared error for the entire dataset, because this is the top node. We also have the entire number of observations in the dataset, and here we have the mean value of the target. So this is the mean house price for the entire dataset. When we take the data one way or the other, these values change. The tree also thinks that the median income is a good feature to subsequently divide the data further, and here it's going to divide the data based on whether the median income is smaller than 3.7. Here we have the squared error of the 11,000 and something observations that are at this node, and this is the mean house price for these 11,000 observations that are at this node. And the same repeats all over the nodes. And when we arrive at the final nodes, also called libs, this value here is the mean house price for the 2000 observations of this node, and this is the value that is going to be predicted by the tree if a future observation makes this path in the tree. So as we see here, median income was selected multiple times. So this is most likely a very important feature. But the question that occupies us is, how do we calculate the importance for this median income? So what we need to do is we need to look at each node individually for this particular split, whether the income is smaller than 5.029. The importance of this feature is given by 1, because we're starting with the whole lot of observations here, multiplied by the squared error, because this is the impurity metric that we are using, because it's a regression problem. And we're going to subtract from the total impurity. So the total impurity is given by the total square error of the data. This is the same that we discussed in linear models. So we're going to subtract from this total impurity the impurity from the left child and the impurity from the right child. The impurity of the left child is weighted by the fraction of observations. So here we have 11,381 observations from the original 14,000 and something. So we're going to weight the squared error by this fraction, and we're going to add the impurity of the right child, which is the squared error 122, weighted by the fraction of observations, which is the 3067 divided the original number. So this calculation here determines the importance of median income at this node. But to obtain the total importance of median income, I need to add the importance of the median income at this node. And just to elaborate this calculation a bit further, I need to treat this node individually. So I'm going to take the squared error, which is 0.828, and here I multiply it by 1 because we are using this number of observations now as the base. And we're going to subtract from this impurity the impurity of the left and the right node, which is going to be given by the number of observations in the left node divided the parent node, this value here, multiplying the square error. And for the right node, it will be this number of observations divided the observations in the parent node, multiplying the squared error. And in order to obtain the total importance for median income, I need to repeat the exercise for this node and for this node, which I'm not going to do here. But basically, the median income importance is given by the median incomes of node 1, which is this one here, plus the median income of those two, plus this median income plus this median income. Then, to calculate the importance of, in this case, average occupancy, I need to do exactly the same calculations for this node here and this node here. And then we have one additional feature in this decision tree, which is the average number of rooms. In this case, this feature is used only here, so we will have only one value to use to calculate the importance of this room. Now, the importance derived from decision trees is normalized to the total importance of the features. So what we need to do next is we need to sum the importance of each one of the features in the classification tree. So we sum the importance of the median income plus the importance of the average occupancy plus the importance of the average number of rooms. This will return the total importance. And now the value that you see from scikit-Learn is the importance obtained from the median income normalized to the total importance, or the importance from average occupancy normalized to the total importance, and the same for average number of rooms. So the sum of the importances of all the features will equal to 1. And this is what you obtain when you use scikit-Learn to derive the feature importance from the decision trees. And we're going to see how to do this in the next video, but I want to nail down the intuition about feature importance in decision trees. Features at top nodes in general will have greater importance because at the top nodes we are obtaining higher decrease in impurity, and features used in multiple nodes are also more important because they have a higher cumulative impurity decrease. Now we need to be careful because if we have features that are highly cardinal, and this is important for highly cardinal categorical variables, the tree will use that feature most likely several times throughout the tree to make decisions. So it is common to find that features with higher cardinality also show higher importance. So with this said, let's move on to the next video where we'll see how to derive all these values utilizing Python. See you there.